All right, mathletes, here we go, 3.7, complex roots. So with complex roots, we need to talk about the conjugate pair theorem, or also known as the complex root theorem. So for any polynomial that function f of x that has a complex root a plus bi is a 0 or a root, then so is a minus bi, its conjugate. Complex zeros always come in conjugate pairs. So remember conjugates. So if this is our complex number, 2 plus 3i, our conjugate just changes the sign of our imaginary part. So our conjugate is 2 minus 3i. Well, minus 5i, the conjugate is just going to be plus 5i. 7, it's just a real number, so its conjugate is 7. And negative 9 minus 4i, again, the negative 9 stays the same sign, but just the complex part changes. Okay, so corollary to this theorem is a polynomial f of odd degree with real coefficients has at least one real 0. And that should make sense because anything with an odd degree is either going to start high and low, and at some point it's going to have to cross the axis, and vice versa. It could start low and high, and at some point it's going to have to cross our axis at least once, if not multiple times. So any odd degree polynomial always has at least one real 0. All right, so we can use our conjugate pair theorem. For given this following information about a polynomial whose coefficients are real numbers, find the remaining zeros of f. So degree 4, I'm going to expect 4 zeros, whether they're imaginary or rational. So I got 1, 2, 3. Well, I'm missing a fourth one. And I know that from my conjugate pair theorem that I have to have my conjugate. So my last 0 is 4 minus I. Okay, so for part B, degree 5, so I have 1, 2, 3, 4 zeros. So I need to find, I have 3 zeros, 1, 2, and 3. So my other zeros are going to come as my conjugates of these. So my other 0 conjugate of 3i is minus 3i. And then 2 minus I is 2 plus I. And there's my other 2 zeros there, or roots. All right, let's look at number 2. So if I want to form a polynomial f of x with real coefficients having the given degrees and zeros, so it's a degree 3, and I know that it has a 0 at 5. I know it has one at 2 plus 3i. So the other one is going to have to come at 2 minus 3i. So there's my 3. So to write out my polynomial now, I'm going to write out my factors. So if I have a 0 of 5, I know that I'm going to have x minus 5 as one of my factors. So remember, I want to write my factor so when this value is plugged in, it's equal to 0. So for that to be equal to 0, I need an x, a minus 2, and a minus 3i. So when this value goes into my x, the minus 2 will cancel out the real, minus 3i will cancel out the imaginary part. And my other root is going to be x. Again, I need to minus my 2, so that stays minus 2, but I need a plus 3i there, and that'll give me a 0 there. Okay, so now that I have my 3 factors, I need to multiply this across. So to get this as a polynomial, I want the polynomials in standard form. So x times x, I get x squared. X times that, I get negative 2x, and this I get plus 3xi. Then minus 2x plus 4 minus 6i minus 3xi plus 6i and minus 9i squared. Well, I need to remember I squared is equal to negative 1. So when I make this equal to negative 1, that's going to make negative 1 times negative 9 is a positive 9. So I'm going to collect my like terms. So x squared, only have one x squared. Okay, notice all the things that should cancel out. Plus 3xi, minus 3xi. Anything with an I we hope will cancel out. Okay, minus 2x, I get minus 4x. And then the minus 6i plus 6i, those cancel out, as did those. And then I have a plus 4 and a plus 9, so I'm plus 13 here. So that still needs to be multiplied by x minus 5. So I'm going to multiply that across. So x times all these, I'm going to get x cubed minus 4x squared plus 13x, and then negative 5 through. I get minus 5x squared plus 20x minus 65. So f of x is equal to x cubed minus 9x squared plus 33x minus 65, collecting all my like terms. So here's my polynomial with all the coefficients identified that has these three zeros. Okay, let's look at example 3. So find the complex zeros of the polynomial function and write f in factored form. All right, so x to the fourth minus 1, we had this, you've seen this in class when we were working on factoring. Well, this is difference of two perfect squares. Well, this is x squared minus 1 times x squared plus 1. Well, this factors nicely. Difference of squares again, minus 1, x plus 1. So I can see my real zeros are going to be when x equals 1 and negative 1. But I need to find my complex zeros. Well, that happens here. Well, when is x squared plus 1 equal to 0? Well, so when x squared is equal to negative 1. So when x is equal to plus or minus the square root of negative 1 is I. So as I write these factors, I'm going to get x minus I and x plus I. And those will be my four factors when multiplied together would go back to f of x, and it's in factored form. Okay. Last example here, example number 4. Use the given 0 to find the remaining zeros of the function. So I have a fourth degree function. I'm going to expect 4 zeros, and I'm given 1. So I need to find the other 3. Well, I know from this 0 I have the conjugate, so minus 3i. Well, what factors are those going to give rise to? So I'm going to get x minus 3i and x plus 3i. So as I multiply this out, I'm going to get x squared minus 3i plus 3i minus 9i squared. Well, I squared is negative 1, so that's plus 9. So collecting like terms, I get x squared plus 9. So I know that that's part of the factor there. So I know that this times something is going to be equal to f of x. Well, to do that, I'm going to divide both x squared plus 9 to this and divide f of x by x squared plus 9. Well, the downside with dividing f of x by x squared plus 9, it's not a linear factor. So I need to do long division here. So I have x squared plus 9 divided to this quartic. So I have 3x to the fourth plus 5x cubed plus 25x squared plus 45x minus 18. Okay, so x squared times what is 3x to the fourth? Well, that's going to be 3x squared. Multiply that through, and I get 3x to the fourth. And then I'm going to get a plus 27x squared. So I need to remember to subtract. I'm going to change the signs. So that goes to 0. This drops down 5x cubed. That 25 minus 27 is going to be minus 2x squared plus 45x minus 18. X squared times what is 5x cubed? Well, that's going to be plus 5x. So multiply that through. I'm going to get 5x cubed plus 45x. Okay, change my signs. That goes to negative, that goes to negative. So this drops down, minus 2x squared. That goes to 0, minus 18. So x squared times what is negative 2x squared? That's minus 2. Minus 2 to that, minus 2x squared, minus 18. Change my signs, add them up, and I get a remainder of 0. So then it does show that x squared plus 9 is a factor of that f of x. So over here, I get 3x squared plus 5x minus 2. So now we need to factor this. So this one should factor out nice. So if I look at this, a times c is negative 6, add to 5, and I get 6 and negative 1. So I got 3x squared plus 6x minus x. And minus 2. Factor what's common out of here. It's a 3 and an x, and I got an x plus 2 here. Factor out a negative 1 so that they're the same. I know I've done this right because I have these two being the common factors. I factor that out, and I get x plus 2 times 3x minus 1. And this drops down is x squared plus 9. And this is equal to my f of x. So to finish this off, I need to make sure I write the zeros. So I know I had the conjugate, minus 3i. And after I factored out the others, I get here. So this is going to give rise to x being equal to negative 2. And this one being where x is equal to a positive 1/3. And that will give me my 4 zeros for this 4th degree polynomial. Make sure you highlight questions and bring them to class tomorrow.